Thanks, Mark, for inviting us to be part of the Quantum Marketplace series. My name's Zach Newman. I'm one of the co-founders of Octave Photonics. We're a small company located just outside Boulder, Colorado, and we're developing nonlinear and visible wavelength photonics like the chip shown on the right. Nonlinear optics is a large field, but in general, it involves the conversion of light from one wavelength to another using a suitable optical material. And typically, addressing optical nonlinearity is only possible when working at the very highest optical powers, but nanophotonic waveguides make it possible for nonlinear processes to occur at much lower powers because the light is confined in a waveguide that's only a few hundred nanometers across. As an example, on the top left is an image of a single ship with waveguides of different widths that generates different colors across the visible spectrum when pumped with an infrared laser. So quantum computers and optical atomic clocks, like the one shown on the top right, require dozens of visible wavelength lasers and optics, can take up an entire room and consume kilowatts of power. So nonlinear photonic chips, like the one shown on the bottom right, can help simplify next generation quantum sensors. But in order to get there, two key problems must be addressed. First, in comparison with silicon photonics for telecommunications, fabrication for quantum photonics is slow and costly, and that dramatically slows the pace of development. And second, fiber optic packaging and integration with electronics is critical. As an example, here's an image of a typical nonlinear photonics experiment where the photonic chip, which is highlighted in yellow, is surrounded by a myriad of free space and fiber optics that are required to get the light in and out of the chip. At Octave, we're developing easy-to-use devices based on our nanophotonic chips. For example, the module on the top left utilizes a nanophotonic waveguide to enable self-referencing of an erbium fiber frequency comb at 10 times lower powers and 10 times smaller volumes than is possible with conventional methods. On the right is an image of a broadband electro-optic frequency comb, where a waveguide is critical for spectral broadening. One of the things that makes Octave unique compared with other nonlinear photonics foundries is that we do full end-to-end product development. This starts with device design and simulation, followed by tape out and in-house fabrication with silicon nitride, tantalum pentoxide, and thin film lithium niobate. We test and package devices, and we've developed specialty packaging techniques for low-loss fiber chip coupling for visible wavelengths and high average powers. And finally, the team at Octave has an extensive background in nonlinear optics and quantum sensors, and we regularly assist with system integration and deployment. In fact, we recently installed one of our electro-optic frequency combs at the Keck Observatory on Mauna Kea. Going forward, we want to push on two main avenues towards making our nonlinear nanophotonics more accessible. First, we plan to build on our fiber chip packaging techniques, making the process more automated, allowing for scaling to large quantities. And we're actively working on both hybrid and heterogeneous integration to allow multiple devices and material platforms to work together in a single package device. And we're developing visible wavelength grading couplers using inverse design techniques to interface chips with free space quantum sensors. And second, we're currently working to establish a nonlinear photonics foundry that offers low volume, low cost chips and could fill a critical need for rapid prototyping to accelerate the design cycle for quantum nanophotonics. In plain English, you could design a waveguide device, order a single chip, and receive your chip within 3 weeks' time. Finally, we're continuing to develop new applications for nonlinear photonics, including microresonator-based devices for both broadband microcone generation and optical parametric oscillation. We're developing narrow line width SPS laser sources, entangled photon sources, and visible wavelength grading couplers and metasurface optics. Nonlinear photonics is in the early stages of development, so we're always looking to connect with partners, collaborators, and customers. So please reach out to us if you're interested in learning more about Octave, and thank you so much for listening. Here's some of our contact information.